Welcome back, everyone. In this video, we're going to continue learning about the basics of organic chemistry. Specifically, we're going to talk about constitutional and structural isomers, the degrees of unsaturation for a molecule, and then understand the difference between the structure and function of alkenes versus aromatic hydrocarbons. So earlier, when we looked at hydrocarbons and alkanes, we talked about how they can either be straight-chained or they can be branched. So what's the relationship that exists between these molecules? While they have the same molecular formula, they are not identical. These are what we call constitutional isomers or structural isomers. These are molecules that have the same molecular formula, therefore they are isomers, but they have different bonding arrangements, different patterns of connectivity. And so if we were to have numbered these carbons, 1, 2, 3, 4, 5, 6, 7, 8, what we can see is that now our longest chain is not 8 long. 1, 2, 3, 4, it's only 5 long. And we've taken perhaps carbons that were once 6, 7, and 8, and we've put them on different locations in the molecule. So it's the same number of carbons and hydrogens, therefore they are isomers, but they're bonded differently. Therefore they have different structures, different constitutions. So they're either structural or constitutional isomers. It's the same idea, but just two different terms. If we can look now, here's some different examples of constitutional or structural isomers. We have butane that can be either straight-chained or branched as isobutane. Pentane can either be straight-chained, have one branch as isopentane, or two branches, neopentane. And then hexane has actually 5 total isomers, structural isomers, depending on the number of branching. Notice that these both have one branch. This has 2 branches, and rather these have 2 branches. And then within these branchings, within the one branch, where the location of the branch is different. So we can see for the first molecule here on the bottom, the branch is on the second carbon, and on the molecule up above and to the right, it is on the third carbon. And so because those have different structures, those are different molecules. They're isomers. With the molecules on the right, they both have 2 branches, as indicated from the fact that the length of the carbon chain is only 4 long. But we have a scenario where the branching can either be on 2 different carbons, 2 and 3, or on 2 of the same carbons, 2. You'll notice, hopefully, that if we were to take this molecule and put the branching instead of on the second, but on the third carbon, 1, 2, 3, 4, that this is actually the same molecule. If we just renumber them, 1, 2, 3, 4, we get the same molecule that we had already. And that's an important thing to pay attention for, because very often students will create extra isomers that are not actually different, and they've just taken the molecule and maybe rotated it around. So let's practice. Which of the molecules below are structural isomers of each other? Pause the video and try this on your own. Welcome back. How did you do it? Hopefully you started by determining the molecular formula of each of these molecules. In order for them to be isomers, they need to have the same molecular formula. Each point represents a carbon, And so what we see is that each of these molecules has 5 carbons. However, we also need to account for the number of hydrogens. And the way that we know how many hydrogens there are is based on the number of bonds that a given carbon atom already has. Each carbon atom has a valence of 4, therefore it will form 4 bonds. This carbon already has 2, so we need 2 hydrogens. This has 1, so we need 3 hydrogens. 2 hydrogens here, and 3 hydrogens here. We see then we have C5H10. When you count up for the other molecules, this is also C5H10, C5H10, and C5H10. However, this is C5H8. So A through E are our structural isomers of each other. Let's now take a closer look at what we're going to call geometric isomers. So butene has a double bond. We can draw the double bond occurring between the first and the second carbon. We can draw it as part of a branch that occurs on the second carbon, or we can draw it having the butene 4 carbons in a straight chain, but a double bond between the second and third carbons. When we draw it in that direction, we actually get 2 different isomers. These are called geometric isomers. And geometric isomers are molecules that have the same arrangement of the atoms in terms of what element is bound to what element, but they have different arrangements in space. The easiest way to see this is to look at these molecules in 3D, and I'll show you that in a little bit. So when we look at these, we have a set of structural isomers, which is 1 butene, 2 methylpropene, and then the 2 butene in general. But then within 2 butene, we have our geometric isomers. And geometric isomers are chemically different from each other. They have their own properties. So let's talk a little bit more about these geometric isomers. We use the terms cis and trans to describe the geometric isomers. And what we're looking at is the location of the groups that are on either side of the double bonds. So for trans 2-butene, if we draw a line through the double bond and we look at the location of the carbon atoms, we see that you would have to go across the double bond in order to get from one to the other. However, if we draw a line through the double bond of the cis-butene configuration, we see that they are on the same side of the double bond. So we don't have to go across it if we were to draw a line to get to them. So the easy way to remember this is that these are cis, and so they make the sound s like S. They're on the same side. Whereas trans, you have to go across, like the Transcontinental Railroad goes across the United States. So why does this happen? Well, we need to remember that the carbon-carbon double bond, it has the pi bonds with orbital overlap occurring on both sides of the bond, or both sides of the atoms. That makes it so it's difficult for that bond to rotate. And because it doesn't rotate easily, these molecules are stuck in their configurations. Trans 2-butene is stuck as trans 2-butene. Cis 2-butene is stuck as cis 2-butene. And they aren't able to convert between the two of them. So let's look through and talk about how to determine whether or not a molecule has a geometric isomer. First thing to do is to find the two carbons that are involved in the double bond. Let's call these carbon A and carbon B. And then we ask ourselves, are the groups attached to carbon A, are they the same or are they different? And we then ask, are the groups attached to carbon B the same or are they different? And if they are different, if 1 is different from 2 and 3 is different from 4, then the molecule has a geometric isomer. So let's say that they are all different from each other. The geometric isomer would take, it's as if we took 1/2 of the molecule, we kept it the same, and then we rotated the other molecule. We swapped the locations of the other atoms, and then we see that the relative positioning of 2 to 4 has gone from being cis to being trans. All right, let's let you practice. Which of these molecules have geometric isomers? Pause the video and try this on your own. So let's evaluate for each carbon. We need to determine whether or not the groups attached to each carbon involved in the double bond are the same or different. On this carbon, they are different from each other. We have a hydrogen and then a large hydrocarbon chain. On this carbon, these two groups are the same, and so this molecule does not have a geometric isomer. This molecule, this carbon is good. It has a CH3 and then a larger hydrocarbon chain. This carbon also is good. It has a CH3 and then a larger hydrocarbon chain. So you'll notice it doesn't matter that these two are the same. That's okay. And that these two are the same. That's okay. What we need is the two groups that are attached to the same carbon to be different. And this is what its geometric isomer would look like. Okay, this carbon is good. We have a large ring structure and then hydrogen. The carbon on the right, this is not good. You'll notice that this carbon and this carbon have the same group. These have the same, and then this is the same because it's the same point. Finally, here, we already evaluated this scenario before. This one is all right. And now that we've put the chlorine on here, this carbon is okay. And its geometric isomer looks like this molecule. All right, let's have you practice again. Which of these molecules can have geometric isomers? Pause the video and try this on your own. The answer here is C. C is the only molecule that can have geometric isomers. We can easily rule out D and E because they don't have a double bond in them. A is ruled out because the two groups on this carbon are the same. And B is ruled out because these two groups on this carbon are the same. The geometric isomer of C would look like this molecule. Okay, here's another practice problem. This one's a little harder. So pause the video here and try this one on your own. Welcome back. This is a little bit challenging because you're trying to identify the molecules. We know that fumaric acid has a trans double bond, and malic acid has then the corresponding geometric isomer, which is the cis double bond. Hopefully, you were able to easily eliminate 2 and 3 because there's no carbon-carbon double bond here. And this is showing a structure. This carbon has 5 bonds. An expanded octet for carbon is never going to happen, so this molecule does not even exist. Now we're looking at the relationship between these groups within the molecules fumaric and malic acid. So if we draw a line across the double bond, and then we say, are the two groups that are identical on the same side or on opposite sides of the double bond? We see that in this molecule, if we look at the hydrogens, they're on opposite sides of the double bond. We'd have to draw a line across the double bond to get to them. They are trans to each other. However, in this case, they're on the same side of the double bond, and therefore they are cis to each other. That means then that this is fumaric acid and this is maleic acid. Let's now talk a little bit more about saturation. So cycloalkanes, alkenes, and alkynes are what we call unsaturated. For a molecule to be saturated, then we have to have the maximum number of hydrogens attached to it that we can have. That involves only alkanes. So cycloalkanes and alkenes end up with double bonds or ring structures, and they actually have the same basic structure. Alkynes you get with a triple bond, and that reduces the number of hydrogens even more. So each ring or double bond or triple bond is going to increase the degree of unsaturation. That reduces the number of hydrogen atoms by 2. So we can see this in a practical sense when looking at saturated fatty acids, such as stearic acid, and unsaturated fatty acids, such as oleic acid. And what we see is that the saturation level is going to affect the properties of those molecules. Because stearic acid is unsaturated, we're able to form linear chains of stearic acid, whereas the double bond in oleic acid forces it to take a kind of crumpled shape. And this will affect the overall properties. Stearic acid's melting point is over 150 degrees Celsius, whereas oleic acid's melting point is at 56 degrees Celsius. That's because there's fewer interactions of the chains within oleic acid. So what we see is that the saturation level is going to affect the properties of those molecules. And as we've seen already, we know that alkenes versus hydrocarbons have different levels of reactivity because of the delocalized pi bonding within aromatic compounds. Because these have delocalized pi bonding, that spreads out the electron density across the whole molecule, which makes it lower energy, and therefore it doesn't react. If we were to take a molecule like an unsaturated fatty acid, we see that that behaves similarly to an alkene and would react appropriately. Then the last thing to review here is we can actually talk about the hybridization of hydrocarbons. So alkanes are always going to be sp3 hybridized. Alkenes are going to have some combination of sp2 hybridization and sp3 hybridization. Alkynes have sp hybridization and then sp3 hybridization, and aromatics are all sp2. Here's a last problem for you to evaluate. We want you to determine which molecules that are shown on your screen have the same degree of saturation. Okay, so you're looking for which of them have the same number of hydrogens that are removed because of either the ring structures or the double or triple bonds. All right, so we know that each ring or double bond adds a degree of unsaturation, and that triple bonds add 2 degrees of unsaturation. So we're not looking at which of these have the same molecular formula, but rather which of these have the same number of double or triple bonds or rings or combinations thereof. So in green, we have boxed in the molecules that have 1 degree of saturation. So what we see here is that a double bond is equivalent to a ring structure. So a cyclic alkane and an alkene both have the same level of saturation. We have 2 degrees of unsaturation shown here. We could either have 2 alkenes or we could have an alkyne. Both of those will have 2 points of saturation, or 2 degrees of saturation. And then finally, we have here a ring structure with 2 double bonds paired with a longer carbon-carbon structure. This fatty acid here has 3 degrees of unsaturation, 2 from the double bonds in the length of the chain, and then 1 from the carbon-oxygen bond at the end. That's it for watching. Thanks, and have a great day.